I'm going to talk about abstractions considered harmful and other opinions about writing maintainable code. And basically what this is just a collection of war stories from the time when I was running a lot of servers that were supposed to be up and running all the time, and sometimes they weren't. And the idea here is that by telling you these stories, you will not have to make the same mistakes as I did. So learn from the mistakes of others. You can never live long enough to make them all yourself. Supposedly Groucho Marx, or it might be Eleanor Roosevelt. As Abraham Lincoln said, don't believe everything you read on the internet. So this is very much a n=1 experiment. So that n=1 experiment is an experiment when you don't have 1,000 subjects or 1,000,000 subjects. You just try it out on yourself and see how it goes. So these are my experiences, and you might not come to the same conclusions as I did. In these examples, I have rewritten the code to protect the not so innocent people that wrote it in the first place. And even though most of the code that I will present today is not code that I have written myself, but that other people wrote and I had to deal with, I have written exactly that kind of code myself many, many times. Yeah, so we shouldn't point a finger at people and blame them. I'll do that in private, but I've done these mistakes myself. And I put opinion in the title because opinions are so much more interesting than facts. But these are not opinions. These are really only the facts that you will get here today. So the title was just to confuse you. So this is true stories, all of them. And it's just fact about life and programming. Good. So we had this big transaction system that was growing exponentially in load every year, or actually it doubled every 10 months when back then. So we in the engineering department were constantly running and trying to get the system to perform better and better while the load was just increasing and increasing. And at one point, we started to see timeouts, that calls that were coming in didn't all complete on time. So when the load reached a certain level, the system couldn't finish the whole transaction on time. And this was just about a month before the Christmas shopping period would start, when we would see the really, really big loads. So we had worked all summer to make the system better. We had actually even upgraded to the latest version of Erlang Auto-P to be really ready for the load that was coming with Christmas. And then suddenly things started to go bad. And as soon as the load went up a little bit, it started losing calls. So, of course, we had monitoring in place, but there were no processes that stood out. We had logs of almost everything, but there were really nothing interesting in the logs. There were just things going slow suddenly. So, to find the problem, or the artificial problem, we had to use GDC. And here is a little bit to put in your tool belt. I have, of course, not built a nice little tool for inspecting your Erlang system through GDB. So you just have to memorize these magic incantations and then use them whenever you need. So by doing this, we could actually attach the GNU debugger to the Erlang runtime system while it was running and taking traffic. And then we could see that, let's make it dizzy, that it was spending a lot of time in the function generating stack traces. And since we had the whole stack in the GNU debugger, we could see that the call stack contained an actional call to the BIF that built the stack trace. So there was someone calling get stack trace explicitly. So that was a bit bad. And what had happened when we upgraded to R15 was that the great guys at OTP had supplied this very nice new feature that you get line numbers in stack traces. So you could actually see where things crashed, which is very, very, very nice. No problem at all. There's, of course, a little bit of cost to that. So while generating a stack trace, the emulator now has to go through some data structures to find the actual line numbers and build a structure on the heap and put the line numbers on the heap in this structure and build a list of all these things in the stack trace. So there was a lot of extra work being done when doing stack traces. So we looked through the source code and we found a couple of places where you explicitly called get stack trace. So there was this one developer that had written some libraries, and he wanted to abstract away some errors that he didn't know how to handle and what to do with. So he had this sort of filter function, which took a function and 2 arguments, and applied the filter functions to the arguments. And if it was match, somehow the function returned true. You would get back a tuple true and the value x that matched in some way. Otherwise, it will return false. But he was afraid that this could crash, so I also added a catch that caught anything. And since if it crashes, you want to know where it crashes and why. So he got the stack trace, because that would be nice when you crash to find the place of the crash. And then threw this thing back as an error with the stack trace. Okay. Reasonable code. And he also had written this all function that could take a list and apply a filter to things. And the problem here was that he was expecting true, and then he would keep the value that he got back. Or it could be false, and then it meant that you shouldn't keep the element x. And then, of course, things could go wrong, so he caught the problem. And in this case, if something goes wrong in the matching, you should probably not keep that element, so we just don't keep that element. Fine. So this way you could filter out elements that in some way matches. And then someone wrote this nice get matches function that used all and a function match. And this function match actually did the Erlang let it crash thingy and said if x is equal to x, then we keep it, then it's true. Otherwise, it crashes. Okay, that's one way of doing it. So combining all these things would mean that when you threw in a list and did this matching, everything worked as expected. If the values x and y were the same and matched, you would keep it. And if they weren't, it would throw an exception, and then it would catch the exception and don't keep the element. So by calling this get matcher thing on a list and something you wanted to match on, you would get everything that matched from the list. It works. It was perfectly semantically correct code. As a side effect, it built a stack trace every time with line numbers. So before line numbers, 40,000 times per second, this was okay for the system. We had some big systems, so doing 40,000 stack traces per second was not a big problem. Adding line numbers to this, it started to take a little bit more time. We were still doing 40,000, 50,000 calls to get stack trace per second, and yeah, things didn't work out so well then. So some of the takeaways from this is that don't throw away errors if you don't know what they mean. That's usually not a good thing to do. And don't get the stack trace unless you're crashing and logging. So this library function that got the stack trace and then threw it back, that is just bad on so many levels. So if you would just have skipped doing that, everything would have been fine. It would have kept on throwing the exception from below up, and things would have worked. Not the most efficient way of doing it, but it would have worked, and not building a stack trace. Another thing just to throw in there is don't use throw when you mean error. So know that throw is for things that you want to do a quick return to some higher place in your program, and you actually want to use that value, and error is when something goes wrong. And don't write lots of layers of libraries hiding too much info. So in this example, I've cut it down to make it fit on 2 slides. And in that process, I removed many of the layers of the libraries that actually hid the fact that you were matching and expecting a crash in one place, and in another place you were not really expecting a crash but handling it. And for the developers using the libraries, it was very hard to see that this was not the way you were supposed to use the library. So everything was abstracted away, and the second developer that wrote the match function that just crashed thought that this was this actually worked. This would give the right result, but it was unclear what the side effects were in this case. And of course, the Erlang principle of it all is just to let it crash, but not when you want true or false. Or don't let it crash if you can avoid letting it crash. Brings us to another story. So I was on parental leave, and after summer I came back, and I said, "Oh, how are things?" "Yeah, they are not okay. Things are working out well. The system is up and running, and so. But when we load code, the system crashes." And that was a bit scary. Okay. Well, it's not every time. Okay. It's about every second time. Okay. But it's not all machines. Okay. So at that time we were running 5 machines, and they were a little bit out of sync. So some of the machines thought it was time to crash at time A, and some of them thought it was okay to crash at time B. And then they kept on ping-ponging back like this, and the master was moved around between the system, and everything was working, and you didn't really notice any problem as a consumer, because it just went to the next machine. But every time we loaded code, a few of the machines just went dead. And we start to see a pattern here. We didn't see anything in the logs. We didn't see anything strange in the monitoring tools. There were no crash dumps. There were no error messages. It just died. Fortunately, when upgrading the system, of course we were doing the nice Erlang way and upgrading the system while they were running and taking traffic and so on. But while we were upgrading the system, we were logging each step in the upgrade process. And it turned out that the problem we had came while we were loading new code for our domain-specific language. So we had this nice little backtracking domain-specific language so that we could write rules to decide on different things. And if some rule failed, it would backtrack up and try another rule. So it was sort of prologue-like thingy. Very nice for writing rules. And it was when loading Erlang-generated modules that was compiled from our domain-specific language that this crashed. So the backtracking was implemented with try-catch. And the problem is that we didn't see anything at all when it died. But when we realized that it was actually when we loaded new code, we wrote a program that just generated and loaded new versions of our generated code. And after a while, the shell died and the beam printed, beam catches cons, no free slot, sad face. So that was nice. Then we had something to look for in the beam source code. And looking just a few lines above this place in the code where it says no free slots, and well, actually we grabbed for the sad face, of course. There was only one sad face in the whole beam code. This was the only sad place in the whole implementation. And a few lines above it said, should use dynamic reallocation. Yeah, no kidding. And it defined the tab size here of something reasonable, like 16 times 1024. So that was how many try catches the Erlang system could handle at the time. So in all the loaded code in the system, it could handle these many try catches, or just catches as they were before try. And the problem when we loaded code, when you load code into a running system, the system keeps the old version of the code. So by loading code, we actually had twice as many basically catches as when not loading code. So since almost all our try catches were in the generated code for the domain-specific language, which had backtracking, we usually doubled up on the number of catches while loading code until the code was purged. So the real problem here was actually how we started Erlang. So we just started up the Erlang system as a daemon without the shell. And then all the standard error output just ended up in dev null. So this nice sad face just went to dev null, and we never saw the sad face. Had we seen the sad face, everything would have been quickly solved. As soon as we found this line of code, we could just fix this by not fixing the real problem, but increasing the size of this buffer. And then it was up and running. Also, as you will see, we fixed the other problem by using run Erl instead, which of course you should use. Everyone uses run Erl, okay? And getting all the output into nice little logs that we could search afterwards. But of course, we were not using the latest version of Erlang. As soon as I looked at GitHub for this, I saw, whoa, Earth's realloc instead of sad face. So the sad face were gone, and instead it reallocated to a larger array, and everything was fine. Thank you, Björn Egel, who checked that code in. So at this time, we should have upgraded to the latest version of the runtime system to avoid the problem. So the takeaway, always use run Erl. Use the latest version of Erlang, the latest stable version at least. Make sure you don't send errors to dev null. And of course, what saved us was the core thing of Erlang that you actually run it on more than one machine. So always have more than one machine. And it's a good thing if they're a bit out of sync so that they don't crash all at the same time. So the next story is about sharing. So not the nice kind of sharing where you give things to people, but the really nice kind of sharing that the Erlang VM does, where it actually just have one copy of everything. So one day our system died. And we could see that now we had actually monitoring and logs in place that showed us something. So we could see that there was a huge peak in memory. So it was using 256 gig of memory suddenly. And we could see actually which processes were using a lot of memory. And we could see that this was an XML parser that actually it was a supervisor monitoring an XML parser that suddenly were using memory. And a supervisor should never use any memory at all, really. But so what happened was that there was a parse error of the XML file, and the parser died. And the monitor got the parser state. And then the state became huge because sharing was expanded. So how many here knows what sharing is? A few people. So I will explain what sharing is a little bit. So in Erlang, you have this really nice feature that a data structure, if you use it in two places, it actually is only kept in one place on the heap. So if you have a list like hello, and you put it in a tuple twice, so you have the tuple T and the list L twice in this, on the heap, you will only have 3 words for this. You will have one word that says this is tuple, and then one word saying this is the list, and then another word saying this is the list, and it's the same list. So you can see in the little picture there how the 2 parts of the tuple actually point to the same place in memory. So this is very nice until you do something like a send, or you do IO, or anything that does a deep copy, because then the sharing is expanded. So then you will get 2 copies of the list. So you can write this little program, share here, share that takes 2 arguments, and builds a structure with a lot of sharing in it. And you run it for a second and then return OK. That's fine, no problem. You can call it with the same arguments and just throw away the result, and it's no problem. You call it with the same argument and you inspect the result with, for example, list to binary, and then you will see how big this structure actually is, and it will just crash the whole VM and take you down. So of course the XML parser were parsing the XML file, and then it was keeping, oh, I have to parse that part, and I have to parse that part, and it kept building this structure of the XML file over and over again, which actually was just pointer back to the same structure. But when it expanded, you got the whole tree of everything that needed to be parsed and checked and so on. So the XML file in the beginning was huge. So this was bad, but it was not really what caused the crash. I mean, okay, we got a huge spike of memory, and it was using 256 gigabyte of RAM, but we had some machines that probably had 1 terabyte of RAM at the time. But no Erlang system had done this before. So we wrote some programs to stress test the system and actually allocate a lot of memory. And it's actually quite hard to allocate 256 gigabyte of RAM. So if you don't want to spend a whole day running the program, you have to think a little bit on how to do it, but it's possible. And we did some different versions of this. And what we found, so one obvious thing is to make many processes allocate a lot of memory in Erlang. But unfortunately, that didn't really show the problem. It was when one process used more than 32 gigabyte of memory, and there were some subtle uint 3264 bugs in the garbage collector, and it just crashed when you use more than 32 gigabyte of memory. And fortunately, we had Rickard Karlsson on the team, so he patched things up and sent them to OTP, which I think more or less took the patches as they were, or wrote their own version. At least nowadays, you can use a lot of memory in Erlang, even in one process. So the takeaway is to avoid pushing deeply shared terms to other processes, because then sharing is expanded unless you use Kostis and his friends version that's not out there. Is it? Is it in R19? It's in R19. You have to turn it on. Okay. So the solution nowadays is to yes. So you might notice a little tinge of performance loss. No one has really seen it, but you might. So therefore, it's not turned on by default. But there is actually a fix that does not expand sharing when sending messages, thanks to Kostis and some other developers. Nikos. Yes. And also don't crash when you hand shared terms unless you have turned this switch on. And also be careful when pushing a system to places where Erlang has not gone before. Don't do it in live systems. Try it out someplace first. What saved us here was, of course, monitoring memory usage and logging the process IDs for almost everything happening in the system, so we could easily find the problem in this case. Yeah, so there in that case, we actually had memory in the system, but one day we ran out of memory. So we had probably 1 terabyte of memory in the machine also at that time. And we did have monitoring in place, and we could see which process did this. We did have logs, and we could see what the process did. It compared 2 sets. Sorry, the complexity of complexity. In the last one? No. The current one, the memory. We're out of memory. Yes. So that's usually a problem. I don't know. Sorry. The problem was that we ran out of memory. Good. Yeah. Okay. So we had a function that compared 2 sets. So a bit simplified. It tried to see if one set of name matched another set of names. Like if I'm Erik Nils Stenman, I say when I fill out my form, but my full name is actually Mr. Nils Erik Morten Stenman. It has to see whether these 2 sets are the same in some way. So basically, it did this by permuting the names that it tried to match with the names that were okay. So some of you can see where this is going. So when you permute a list, you get n faculty different list. So for 5 names, like most people have, or something like that, it's not a big problem. You have 120 lists. But you compare, of course, with 5 names in the solution list also, and you get 14,000 combinations. Okay. If you have 7 names, you suddenly get up to 25 million combinations. And if you're some Finnish person with 12 names, you get 2.3 to the power of 10 to the power of 17, which I don't really know what it's called. It's like 230 quintillions or something like that. What? Yes. So just know your algorithms and don't permute. So I simplified the problem and the solution a bit here. There were some details that actually made the make a permutation a good idea at some point. But imagine what would have happened if someone would type in their name with a space between each character. Yeah, not so good. So the takeaway is know your algorithm and don't do permutation. And if you really have to get every permutation, then do it lazily in some way. Don't generate everything in advance. And if you're going to compare one permutation with the set, you don't need to permutate both sets. But that's just a little drop in the sea of data. So I'm not going to give you a real story on this one. I'm just going to tell you that this is the way it is. So domain-specific languages is not for your own domain. Don't make up your own domain-specific language. I know, it's fun. I do it all the time myself. But don't do it. So the thing and really the whole point of this whole talk is that you write your program once, and then it's going to run for years, and it's going to be read thousands of times of poor people that have to try to keep it alive. And they would really like to understand your program. And when you make up your own language and use your own language, then someone who comes and wants to understand your code has to first learn your language. And that is not a good thing. So there are some languages that make this very simple, like Scala, which I worked on actually making sure that Scala got out in the world, and Scala 1.0. And we had this fantastic feature where you could define your own operators, and you could, I loved it. I made all these little nice languages for everything, which no one else, of course, could read, because they would first have to understand your language. Elixir also makes it easy. I love Elixir. Use Elixir, but do not start writing your own languages in Elixir. In Erlang, you can, of course, do this with parse transforms, for example. Don't do it. So there are a few places, I'll come to that later, when you actually can do it, but most of the time. So when you write your comments, you write them in English, because that way most people can understand it. The code is in Erlang and the comments are in English, so you can understand it. That's why you do it. That's why you keep to one language. You don't invent your own language for your comments either. That would be silly. Another fact, don't use callbacks, because it makes code harder to read. So this first example there, I actually wrote just the other week. List existing atom binary to list of a binary calling type. And of course, a few days later, my colleague had to understand this, or actually, he had to realize that there was a new function in the callback interface that was called type, which he couldn't really see. So that's not readable. The CB where you get a callback module as an argument and a function as an argument and arguments as arguments. This gets really confusing when you try to read. What does this function do? You have no idea. It calls something with some arguments. You will be very happy when you read that code. And don't use macros either. So this is also code that I wrote at some time. I needed to insert timers at the start of some operations. So I just defined these wrapper function and I used macros because I wanted to have the line numbers correct when things happened in the log macros. And it was very nice. I could save a lot of lines of code at the end there when I wrote the new page PDF that just called wrapper1 and export just called wrapper1 again and so on. Very easy. But writing it out, it's not much more code to write. And now you can actually read the code and see what it does. So that's basically it. Be direct, be explicit, and I don't mean in the rude sense, but in your code when you write it, try to avoid these kind of abstractions which will hide the meaning of your code from the poor reader of your code. Logging you should use everywhere and tag everything. So what we did, we tagged all the log messages with the process identifier, but also you want to, if you have some kind of transaction or something that is threading through your system, you should invent some unique tag, a gensim thingy, a ref, anything that can follow your code through and log it with it so you can find out which message is connected to the log. And don't invent your own syntax, your own language. But there are some places where you can actually embed other languages in your language. And that is when there is a well-known other language, like JSON, for example. So when JSON is well-known enough so that if someone has to understand JSON code, he can read books about it and actually learn how to read JSON code. So you could embed JSON into your Erlang code when you need to generate JSON structures. Or the for the match specification and these kind of things, you can invite your own syntax when it's well enough used, not for your own things. And of course, it's very hard to avoid callbacks if you want to have a system that can be configured in some ways. But the first thing to do is, of course, to use behaviors. So there are some new nice syntax and ways of doing behaviors in Erlang, where you can actually type them also at the same time. So you can have this game behavior with the init, action, get state, and type functions. And then you can use this in a implementation of this callback. When you use this, you can actually also make an explicit module for all the calls. So you don't have to see this m:\f args in your code, but you can actually call the function call game with the function init and send the module as an argument. And it will be much more explicit what's happening. And you can also, if you have to do something with the module, for example, it comes from a database and is a binary, then you can explicitly, in that code, unwrap it to binary to list as existing atom. And then you will have, instead of list to existing atom binary to list b : type, you just see call game b type b. So you see that you're calling the game callback module, you're calling the function type, and you're doing it with some binary that you got from somewhere, but which will actually be the module. So final takeaway is from XCOCD as almost always. This is a thing where we now in our company, not the company that had all these big problems, but this little small company where we just have fun, happy hacking or happy studios. We just have to say, pass me the salt, and then we know that we have to actually do some work and solve the real problem. So this is, can you pass me the salt? Then 20 minutes later I said, I know, I'm developing a system to pass you arbitrary condiments. I can't say them. It's been 20 minutes. It'll save time in the long run. And if you hover over this, it says, I find that when someone's taking time to do something right in the present, they're a perfectionist with no ability to prioritize. Whereas when someone took the time to do something right at the past, they're a artisan of great foresight. Yeah, so that's the way it is. But you will always have to do it right now and not just patch the size of the array to make it load. So the big takeaway is that when your system crash, the first symptom that you find is just the tip of the iceberg, and then someone will spend nights and days and nights and more nights usually hunting down the real cause of the problem. And if you have written readable code, it will go so much faster. So please write readable code for the poor system maintainers. Thank you. Any questions? Simon?
So math and code and all have callbacks.
Yes, it's terrible. Yeah, exactly. Well, so at some point, it's obvious what it does when it becomes good enough. You just have to use your fingertipsgefühl, fingertoppskänsla in Swedish. I think it's German in English, but yeah. So I've always used to like all these higher order functions and so on, but it doesn't make the code more readable in most cases. So it's sometimes a pain. Another question, Simon?
So what's a DSL? It's just a library, right? It's just a library of functions that you can call, like any other library of functions you can call. So when you're saying don't use DSLs, are you saying don't use libraries?
No, so the thing is when you write your own language, invent your own language, and you write your own syntax inside another language. So suddenly in your Erlang program, you're starting using your own language.
Oh, so you mean your own syntax, which you're going to parse and compile and everything?
Yeah.
You're not talking about a DSL in the sense of an embedded domain-specific language.
No, so they're really embedded, so that suddenly in the code there's another syntax.
Oh, okay, fine.
And another semantics of things than the code that you were reading.
But you're okay with embedded DSLs,
yeah,
where they're essentially just libraries?
Yes.
Okay.
Well, it depends. Any other question? It feels like I'm back at my PhD defense here. So Simon asking me questions. Of course, Kostis will also start asking questions now. Okay. Any more questions? Oh, let's thank the fantastic speaker then. Whoa! Woo, 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 woo.